So I wanted to make a video giving tips on problem 5 for the written practice 2, specifically because in my previous videos when I mentioned the solution functions would be responsible for finding, it's not the type that's talked about in 5, and that's part of why there's this hint given on part C. So anyway, we'll get there. Let's just run through problem 5. I'm going to change the numbers, but it'll be similar in spirit, and hopefully it'll give you enough of a starting point. So, okay. What's going on? So first we need to write down the discrete time dynamical system and initial condition. So for my scenario, in fact, the whole Tylenol dynamical system in my previous videos works. So let's just run with that and do what they're asking in problem 5. So in my Tylenol dynamical system, each 6 hours, I excrete 50% of my medication, of the Tylenol, every 6 hours, each 6 hours. And then I take 1,000 milligrams every 6 hours as well. Okay, so now what's the discrete time dynamical system? Well, I guess it also depends on my initial dosage. Let's say I was originally in a lot of pain, and my initial dose, so let's do C for concentration of Tylenol, and 0, so C0 is my initial concentration. So this is just how much Tylenol was in my body. I'm going to take 3,000 milligrams. So we'll use units of thousands of milligrams, so I just have to write down the number 3. Okay, now as far as my updating function, so 6 hours later, so C sub t plus 1, in the span of 6 hours, I lose half of whatever the concentration was. I'm excreting half of it, my liver processes half, whatever. But then I take a pill that has 1,000 milligrams. So I have this 1/2 of my old concentration plus 1 because I'm upping by 1,000 milligrams. Okay. So if we look at what's desired, it's write down the DTDS initial condition. This specifies, so by this I mean updating function and initial condition, that completely specifies my discrete time dynamical system. With just these two pieces of information, I can start to generate my list of measurements. So I begin with 3, and then I plug 3 in here. Let's see, so 1/2 of that is 1.5, and I add 1, I'll get 2.5, and I plug it in again, I'll get 2.25, and I can keep on going, okay? So, let's get rid of this little arrow. That's going to be very similar to what you have to do in part A. Part B, iterate your DTDS to find the concentration of medication on day 7. Graph your values as a function of time. Okay. So, I need to iterate this. Let's go ahead and just keep on going. And this is where, the mathematician in me really comes out, because instead of writing 2.25, I'm going to do 2 1/4. So when I multiply that by 1/2, I'll get 1 1/8, and I add 1, I'll get 2 1/8. 1/8. Okay, and similarly, multiplying by half again, that 1/8 will become a 1/16, and so I would have 1 1/16, and I add 1, I'll have 2 1/16. Let's see, this is 0, 1, 2, 3, 4, so 2 more to go. Okay, so the 1/16 will become a 1/32nd, and then the 1/32nd will become a 1/64th. All right, so all these values, let's change my color. Going from one to the next, all I'm doing is plugging in for C sub t, and then my output is the next thing, okay? All right, but I want to graph these with respect to time, and so that's where these lower numbers are, because these are measuring how many 6-hour increments go by. And so right here is C sub t. Okay, so let's go ahead and plot these. So again, I'm going to do that plus sign and then table. And I have 0 gets paired with 3. 1 gets paired. Oh, you know what? Let's make our life easier. I'm going to put down my updating function. So this is 1/2 x plus 1, right? And I don't need to graph that. I don't care about that. But when I plug 3 into my updating function, that's going to be my 2.5. And when I plug, let's do this again. So now I don't know what f of 3 is because it doesn't tell me in that situation. But regardless, I can still plug that into f. So now I have f of 3. And it turns out that's going to be a quarter. Let me show you what I mean. So f of 3, Desmos is telling me that's 2.5. So I could say, hey, what's f of 2.5? And it's 2.25. But I could just as easily tell Desmos, hey, tell me f of 3. And notice it's still 2.25. So I'm referencing this value here, and I'm using it as an input. So I'm just being very sneaky with that. Okay, so 3, I have f of 3. 1, 2, 3. All right. And if you don't like that, you can just use Desmos to tell you what these values are. Right? I could replace this with 2.5. Similarly, I could replace this with 2.5, or I could replace it with what it is, which is 2.25. Anyway, so let me arrow over. We have 4, we have 5, we have 6. Now, the fun thing about leaving this all in terms of f of 3, so let me change this back to f of 3, is that if I change my initial condition, all right, well, let me go ahead and finish out. So let's see, this is going to be 4 f's, 2, 3, 4, and I have a 3, 1, 2, 3, that's good. Okay, and this will be 5 f's, 4, 5, 3, 1, 2, 3, 4, 5, and where am I at? 0 through 5, I need one more, so add 2, 3, 4, 5, 6, and then 3, and there we go, 2, 3, 4, 5, 6. Okay. So now if I want to see how my initial condition changes things, I've actually programmed this in such a way where, let's suppose my initial dosage of Tylenol was, well, okay, let's just pretend it's not Tylenol, because if I say I took 10,000 milligrams, that's really dangerous. But, dang, okay, hold on. Let me give maybe a letter to this. Let's see if this will work on Desmos. And we'll go here and here. Let's say A equals 3. Now, if I make these all A, this is what I want to do. A, 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 A. So A represents my initial dosage, and I've programmed this in such a way where it will compute all the rest of the values as needed. And if I make my initial dosage 10, you can see how that changes all of my later values. And if it was 8, and there we go. So it's a little easier to see the shape of this graph when I use a larger initial dose, which is why that in your homework exercise he gives you 10. In more realistic settings, like with the Tylenol, I had initial dosage of 3. We can make it look more dramatic by just changing the scale of the y-axis. I can make it look more like an exponential decay, which is what's really going on. Okay. So let's go ahead and I'll just take it home, and we'll just use initial dosage of 10, and I'll go ahead and just change this. So the scheme of Tylenol, I mean, I never actually wrote down what it was. It no longer applies because you do not want to take 10,000 milligrams of Tylenol. That would be lethal. So just some kind of medication. My initial dosage 10. I have a half-life, and I'm going to re-up with 1,000 milligrams every 6 hours. Okay, so let's do this. And now I've plotted it, and my x values are time, and my y values are concentration with respect to that time. Okay? So that is parts A and B. And oh, he says on day 7, so I suppose I should do one more iteration, but day 6 is good enough. All right, now find a solution function. Okay, so this is where things get really sneaky. Now, since our updating function has this constant multiple of 1/2, that for kind of deeper reasons is letting us know that our solution function, so if I were to write c sub t as a function of t, right, versus what we have here, we have c sub t plus 1 is a function of c sub t. Okay, so here's an updating function. This would be a solution function. And it's bad etiquette in mathematics to use the same function name for two different functions. So if I use f for my solution function, I don't want to use that for my updating function, so maybe I should write something like g. That's fine. But in any case, my input for my updating function is different than my input for my solution function. My solution input's time, my updating input's concentration. But okay, let's get back to solving for the updating function. All right, the whole idea is this 1/2 is trying to let us know that there's going to be a 1/2 to the t. And we might use graph transformations to move this around a bit. Maybe there's a coefficient out front. Maybe we have some kind of vertical shift going on, so plus some b. And I suppose if we wanted all the realm of possibilities, I could input even more parameters, but it turns out that this should be good enough. Okay? So, with that in mind, if we look at, let's take away these points for a moment, and let's look at a plot of what 1/2 to the x or to the t looks like. Okay? So it has this exponential decay shape, and notice that it tends towards 0. All right? Now if we go back and plot our data, what does our data tend toward? Well, it looks like it's tending toward 2, right? If you kind of count those horizontal stripes. So let's go ahead and take this function here, and let's just add 2. Let's shift it up. Okay. So now that has the same horizontal asymptote. They're both trending toward 2, but they have different y-intercepts. So let's pop back over to algebra land, and we're dealing with something like 1/2 to the t, or x over in Desmos, plus 2. And this is where that coefficient here is going to come into play. If I plug in, so this is my solution function, okay, f of t. If I plug in 0, what I'm supposed to get out of this is c sub 0, which if I update, so c sub 0 is 10, so none of these measurements really apply anymore. That was from an old time. I should get out 10. All right. But on the other hand, if I plug in 0, what do I actually get? I have c times 1/2 to the 0 plus 2. 1/2 to the 0 is just 1, so this is really c plus 2. So I can move the 2 over, and I find out c is 8. All right, so let's hop back over to Desmos. And I'm trying to make this fit, and I do 8 times, and notice these curves fit perfectly. So, I'm sorry I switched up my initial conditions on you. That's because I wanted my data to drop more rapidly so it'll show up. If I go back to the old initial condition of 3, then let's do the same process again. And this time my little scribbles over here, they don't actually apply. By little scribbles, what I mean, where's my highlighter? There we go. When I scratch this out, these are actually now the values that are plotted on the y-axis on Desmos. So ignore that scratch out. But what does change, right? Now if you notice, I'm still trending toward 2, so that plus 2 that I've added on, that's fine. But my initial value is now 3, it's not 10. So this should be a 3. And if I plug in the 0, into my solution function, then again, that's 1, and so I have c plus 2 has to equal 3. So in this case, it turns out c should be 1. All right, so we can hop back over here to Desmos. Let's make that 8 a 1, and it fits perfectly. So, to recap, when we have an updating function of the form new value is equal to some coefficient times your old value plus some other constant, okay? Or let me actually, I'll use a and, or we'll do mx plus b. There we go. So when we have an updating function of this form, then the solution function has a, let me back this up a bit. The solution function, x sub t, is equal to it's going to be m to the power of t, okay? You kind of, something like this, if there was no plus b. We've seen this before, I talked about in previous videos. Here the solution function would be x0 m to the t, okay? And this type of exponential decay, it just dominates so much that when we have this plus b, we still have the same general exponential shape, but we might have a different coefficient out front, and we might have to shift a little differently. I shouldn't use b because this b is not the same as this value here, so let's use s for shift, okay? So that's the main takeaway, and then you have to play around to figure out what these values are. All right, and let's see if that answers everything. So iterate your GTS, graph values did that. Find a solution function. All right. So back when my updating function was this, and my initial value was 10, that was when my solution function was 8 times, oh, let me change my initial value, sorry. Oops. Okay. 8 times 1/2 to the t plus 2. When my initial value is 3, then my solution function is just 1/2 to the t plus 2. Okay. All right, that's it for this video. Good luck.